Hi, my name is Joseph Zhang, and this is my lab report on uniform motion in one direction. The purpose of this lab was to observe an object moving at a constant speed in a straight line, analyze its motion using a tracker app that we use in class, and then comparing that data with a computational model that we created in GlowScript based on Newton's second law, also known as the momentum principle. So, the main physics principle here that we use is the momentum principle. Net force equals the rate of change in momentum. In equation form, that would be F net is equal to delta P over delta T. If the net force is zero, momentum stays the same, and because of that, velocity also stays the same, as momentum is shown by mv, or m delta v. This is what we would call uniform motion. The object moves in a straight line at a constant speed. Our main finding was that the position versus time data from the tracker produced a straight line, and when I modeled the motion in GlowScript, when we assumed that the net force was zero, the two matched pretty closely, and that confirmed our assumption that the object was moving at a constant velocity. So this is our model. So our system surroundings assumptions. Our system was a rolling battery. Our surroundings included the table surface, air, like air resistance, people standing around the experiment, potentially causing vibrations and whatnot to the experiment, and the person actually rolling the battery. And our assumptions include negligible air resistance, there not being friction, the battery moving in a perfectly straight line without any deviation from the x-axis, and the fact that the table is perfectly level. These are assumptions that we're making. So, the computational model starts from Newton's second law. In GlowScript, I used the starter code. That was given, but we set the net force equal to zero. That means that the velocity stays the same at each time step, and the position is updated linearly. As shown right here, we have the vector set equal to 0, 0, 0, and this causes the ball velocity to remain the same, which causes the ball position to increase at a steady rate. So this basically proves our straight line theory. So for our experiment, we placed the object on a pretty flat surface, and we recorded it moving across the screen at a constant speed. And to calibrate it, we placed a beater stick actually in the frame, and we set it equal to 1 meter, so the tracker can calibrate. So this is our experiment. Basically, it starts from here. We blow on it, and it moves across the screen. And we're also assuming that, or also ideally, we're assuming that the camera doesn't really move. So, using the tracker, I marked the object's position frame by frame, which was every 0.23 seconds, and this gave as you can see down here, this gave us a table of time versus position versus time. And the initial conditions included the object starting point being at the origin, and since the slope is theoretically constant, the slope is also used as the initial velocity. Additionally, the data collection does not start from the beginning of the recording, as the velocity in the beginning is not constant due to the force we initially applied. So the results from the tracker shows a mostly linear relationship with minuscule deviation, and I put a line of best fit in there to show how much it's deviating, and it's really not. And in comparison, we can see that our theoretical is actually a little lower than our tracker data, but it's pretty similar in the sense that they're both in straight lines, and which makes our assumption that the force is equal to zero. So here are some potential errors. The drop-off can be credited to assumptions that we made not being entirely accurate, like the table being completely level, which could have been inaccurate. Also, the battery started deviating slightly from the x-axis, so it was moving both the x and y direction. Also, human error can be accounted for, as you can see in the screenshot I provided below. The point that we put on the battery wasn't entirely on the same spot of the battery every time, so this causes a difference. And also, the calibration stick could have been off by a couple pixels too, which also makes a difference. So what if the axes were flipped? The slope of the graph would change, but the magnitude of the slope would remain the same. So what does it mean if the net force is zero? It doesn't mean that there aren't any forces, it just means that the forces are being canceled out. So the push forward is getting balanced out by the friction, and the gravity is being balanced out by the normal. So here we can see that it demonstrated Newton's first law. Newton's first law being that an object in motion stays in motion. We can also see that by comparing our experimental model to our tracker model, it kind of like validates that principle. So in conclusion, the lab confirmed that an object with no net force stays in a straight motion, and the tracker pretty much matched the model, computational model perfectly, and this shows that the assumptions we made are reasonable.